Hi everyone, we're going to do another video, and this one's mostly going to be dealing with this example here, and it's another algebraic function. It's not a rational function because we don't have a polynomial on top, but we have something involving a square root of a polynomial on top, and we might guess that this might limit out or level out as x approaches infinity or negative infinity, because essentially what we're talking about here is, if we think about the square root of 4x squared over x, just looking at the leading terms, kind of like we had seen with polynomials, that this is roughly speaking going to be approximately equal for large positive x, 2x over x, which is 2. All right, now there's some nuance to this. All right, we got to be a little bit careful here. So let's just verify that algebraically or graphically first, and then we're going to come back and look at this a little bit more algebraically. So here's the graph. All right, I've got this done in Desmos there. And this gap in the middle is because that is not defined between these two values, all right, between 1/2 and negative 1/2. We could show that, right? That quantity inside the square root would be negative there. But as we go and pan to the right, it seems like it's getting closer and closer to a fixed value. What value are we talking about? We can hopefully see that right here. That's 2, right? So it seems like it's getting closer and closer to 2 as we go to the right, and as we go to the left, it seems like we're getting closer and closer to negative 2. All right, and that is going to be the case. We're going to show that explicitly here now. All right, and this is going to take use of this fact that we can actually have a formula for the absolute value, which is that the square root of x squared is equal to the absolute value of x. Let's do a quick check with that and show that that's actually the case. Let's plug in a number. So let's plug in a number, say like -6 here. If you plug in -6, what happens to this expression? Well, you're going to square the -6 first. That's going to make it positive, and that's why this works out, because it deletes the negative, and then we just get +6. So you take the original, which is a negative number, and you end up with its positive result. That is happened by negating it, essentially. All right, so that is true. If we take the square root of x squared, it's equal to the absolute value of x. All right, now what is that going to equal? Well, if x is greater than 0, then we know that the absolute value of x is just going to be x. Now we have a new formula for the absolute value of x, so the square root of x squared is also going to just be x. If x, on the other hand, is negative, then we know that the absolute value negates it to make it a positive quantity. And that's going to tell us for negative x values that the square root of x squared is going to match the absolute value if x is negative, and that's going to be the opposite of whatever that number x is, or that quantity x is. Okay, now how are we going to utilize that? We've seen in some of our other work for the semester that we have to rewrite expressions by oftentimes multiplying and dividing by, or multiplying by a convenient form of 1, or adding in a convenient form of 0. In this case, we want to divide the top and bottom by the same quantity, which is like multiplying by 1. And we want to divide the top and bottom by x, right? Well, x is equal to the square root of x squared. So we're going to do top and bottom by x, but on the numerator, we're going to rewrite the x as the square root of x squared. All right, I'm just going to give myself a little bit of space here. Let's bring this down. And let's do some of this rewriting here. So again, essentially what we're saying to do is, in the denominator, we're going to divide this whole quantity and divide that up by x. In the numerator, we also want to divide that quantity by x, but we're going to rewrite the x as the square root of x squared. That's going to allow us to use some properties of square roots. All right, and that's going to allow us in the numerator to bring that division by x squared inside, and then divide each term by x squared. In the denominator, we're just going to get x over x plus 2 over x. And then we will get, simplifying, limit of the x squares cancel, we're going to get 4 minus 1 over x squared, and 1 plus 2 over x. And hopefully it's pretty clear from here that these terms that I'm going to circle are going to approach 0. those terms are going to go to 0, and therefore we're just going to end up with, in the limit as x goes to infinity, the square root of 4 over 1, which comes out to exactly positive 2. All right, so that matches what we saw graphically. Let's take a look at the limit going towards negative infinity now. That's going to be slightly different, okay? And we got to be a little bit careful with that. All right, so again, what we would like to do is to divide the top and bottom by, and do the same kind of trick to bring in the square root of x squared. But just keep in mind that the square root of x squared, when we're talking about a negative number x, is going to be equal to negative x. All right, so when we do this here, we are going to divide the top and bottom by the square root of x squared. That's, again, like multiplying by 1. We're doing that division in the top, and we're doing that division in the denominator. But in the denominator, it's going to come out a little bit differently. So now we're talking about, again, a limit as x is approaching negative infinity. Oops, didn't write my negative sign there. In the numerator, we're going to get the same thing. So the x squared is going to go inside the square root. We're going to get 4 minus 1 over x squared again. That's fine. In the denominator, no, this is really like x plus 2. The square root of x squared is equal to negative x if x is negative, like it is in our case. And then, simplifying this one more time, we're going to get the limit as x approaches infinity, or sorry, negative infinity, of the square root of 4 minus 1 over x squared, all divided by negative 1 minus 2 over x. And like we've seen before, these terms are going to approach 0 as x approaches negative infinity, and therefore the overall limit in this case is going to be negative square root 4 over 1, which this time comes out to negative 2. Okay, so that takes care of that example. Let's start the discussion on limits involving transcendental functions. So I'm going to switch pages here. Limits at infinity of certain transcendental functions. Let's start out with inverse tangent. All right, and it's got a different limit as x is going to positive infinity versus negative infinity. Looking at the graph here of arctangent, we can see it definitely does level out going left and right, and it turns out it's going to level out at pi over 2 and negative pi over 2. All right, those are some important limits for us to know, and something that is very useful and comes up fairly frequently in math. Now, again, this is saying we have those horizontal asymptotes, so those are what those limiting values are. All right, so what are we seeing here? As x goes to positive infinity, it's going towards pi over 2. As x is going to negative infinity, this is approaching or leveling off at negative pi over 2. For exponential functions, all right, we should know what the graph of this exponential function looks like. So I'm just going to give it a quick sketch here. The base being positive, it's going to be exponential growth up to the right, down to the left, and therefore our limit is going to be non-existent, or we're going to say infinity as x approaches positive infinity. It's going to be 0 as x approaches negative infinity. For 2 to the x power, all right, now we have 2 to the negative x power here. Now keep in mind here, when we have 2 to the negative x, that's the same as 1 over 2 to the x, all right, which is the same as 1/2 to the x power. So our base is less than 1, so we're going to get a little different scenario happening here. This time this is exponential growth. Okay, and oftentimes we write 2 to the negative x just for space sake, understanding that that's the same as 1/2 to the positive, or 1/2 to the positive x. So this time we have the opposite result. It's going to approach 0 as we approach positive infinity. It's going to approach infinity as we approach negative infinity. Generalizing that result, what are we going to see? If our base is bigger than 1, then we're going to have those same two results. We're going to go up to the right, down to the left. If your base is less than 1, then you're going to be going down to the right and then up to the left. And then those are our limits at infinity in that case. Let's look at specifically the base e, because base e comes up a lot. And we're assuming, okay, we've got some positive number k, and what we're focusing our attention on is e to the kx or e to the negative kx. Well, if k is positive, then we're still talking about exponential growth if it's e to the positive kx. So we're going to be back in your exponential growth phase. If you're talking about e to the negative kx, it's going to be exponential decay, because again, that's going to be 1 over e to the positive k. And we're going to be in this scenario. Okay, so hopefully that's clear from the graphs that this is what we have going on here for powers of e, or limits at infinity involving e, possibly raised to numerical powers times x. All right, now let's look at these two examples here to wrap this recording up. We've got the same function here, but we just want to know what happens as we go to positive infinity versus negative infinity. Well, we can't just think about going towards infinity for this first one, because this is going to approach positive infinity as x is going to positive infinity. So the idea for this problem is we're going to have to do a little bit of rewriting before we can analyze the limit, and we want to divide everything by e to the 2x power. All right, doing that will give us the same limit. And I'm going to pause and then come back in a second. So just to save time in the recording, I wrote that out. All right, so we're dividing top and bottom in each term by e to the 2x. Now what's going to happen here, we're going to get these to cancel out, and we're just going to therefore get 8 over e to the 2x plus 3, and then 7 over e to the 2x plus 5. And what do we see therefore happening? These terms we know now are going to go to 0 that I'm circling. Those terms are going to approach 0 as x gets bigger and bigger and bigger, and therefore the overall limit is going to be just 3/5. We can verify that graphically also. It's not going to happen when we go to the left, though. When we go to negative infinity, that doesn't happen. And we don't need to actually do anything here, algebraically speaking, because as we showed above, as x is going towards negative infinity, that's exponential growth. So going backwards, these terms are going to approach 0. All right, and therefore the overall limit in this case is going to be 8 over 7. All right, again, you could verify this graphically. All right, in the next recording, we're going to do a little bit more with limits at infinity involving e.